Okay, this is Dr. Matthew J. Trom. As promised, I'm going to work through this dynamics problem that we did in class but didn't get all the way through. And I'm going to start over from the beginning. So if you, for whatever reason, didn't see the description in class, you can watch all the way through here. So the idea is that I've got an RC car and I've got one of our RC car shock absorbers attached to the chassis of that car. And this shock absorber can basically do two things. I can squish it, so squish it, squish it, squish it, or the shock absorber can actually rotate along this point through an angle theta. So it basically can move in two different ways. And the question that I'm trying to sort out is how to write the equations of motion for point P. That's right here at the end of the shock absorber. Maybe there's a wheel or something attached here. But the equations of motion for point P in the reference frame of the RC car. So like a driver, for example, we have a little miniature stick figure here sitting in the RC car. So from this person's perspective, how does point P move? So that's the goal. So write the equations of motion that describe that. Now there's a few things that I have to set up before I can begin to solve this problem. The first is that I'm going to write down the reference frame transfer theorem, which I'm going to refer back to a couple of times. So the reference frame transfer theorem goes as follows. So it's the derivative of some vector in what I'll call reference frame G with respect to time is going to be equal to the derivative of the same vector in reference frame A with respect to time plus the rotation from one reference frame to the other reference frame cross that same vector again in the G reference frame. Okay, so that's my reference frame transfer theorem. Okay. The next thing that I need is to recognize that in this reference frame transfer theorem, there's this thing called omega. Omega is a rate of rotation between one reference frame and another. I am going to have two reference frames here, which I'll describe, but I need to figure out what this omega is. So let's figure out what the reference frames are. So the first reference frame is kind of the easier one, which is the reference frame of the driver sitting in this RC car. So we're going to call this G. So that's our first reference frame. We discovered in class that G is for ground, so G for ground. And then the second reference frame is going to be a reference frame that's basically stuck to point P here. So a reference frame that rotates and moves with point P. So I'm going to call that, we'll call that A. So that's a second reference frame. And good rule of thumb, if you're trying to figure out how many reference frames you need for a particular problem, is you look at the number of rotation opportunities, rotation possibilities, and add one to that, and that gives you the number of reference frames. So in this case, we've got the fixed reference frame, and then we've got one opportunity to rotate around that reference frame, and so that suggests that we need two reference frames, and that's it, right? Because there's 1 degree of rotation, and so 1 plus 1 is 2, one reference frame, two reference frames. So that's where we need to stop. We don't need to add any additional reference frames. There was a question in class about, well, doesn't point P not only rotate but also translate, and therefore shouldn't we have an additional reference frame associated with the translation in P? And the answer to that is it turns out that we can use some neat little vector tricks, which I'll show you here in a second, to represent the translation of P in reference frame A. So we don't need an additional reference frame for translation, only for rotation. So that's the answer to that question. Okay, so we've got our two reference frames. Um, and we were again trying to figure out what this omega value is. Omega is just the rate at which reference frame A is rotating with respect to reference frame G. So I'm just going to write that down. I'm going to just say, just to remind myself, that omega from G to A is equal to the rate of rotation. Well, I know theta is the position at any moment in time. So the derivative of theta with respect to time, d theta dt, is going to be omega, that rate of rotation. So I'm just going to write this more simply here as just theta dot. There we go. And so that's a representation for omega. Now I do need to describe, because omega is a vector, right? That's what this line represents. I do need to describe the direction of theta dot, but I don't yet have enough information to do that. So I'm going to just sort of leave a little line here to remind myself that I need to come back and give this a direction once I know how to do that. So that's the second piece. So first piece is reference frame transfer theorem. Second piece is to figure out what omega is. And the third piece is just to remember the product rule. So product rule, we had some discussion in first period whether the product rule and the chain rule were one and the same. I think that might still be true, but I was convinced, at least for purposes of this problem, that product rule and chain rule are two different things. So I'm going to call this a product rule because that's what you guys seem to have learned it as. So the product rule is just when I have the derivative of a product, so a times b, where both of those are potentially variables. And I take the derivative with respect to something else. I need to take the derivative of the first term times the second term, and then I need to add the first term times the derivative of the second term. And that is going to turn out to be quite useful. We're going to use that at least a couple of times in this problem. Okay, so I've got most of the pieces now. The first thing that I need to do, we'll call this, we'll maybe put it here, we'll call this step one. So step one is to select my origin and my coordinate system. And I have to do that for each reference frame. So I'm going to have one set of selections for reference frame G and one set of selections for reference frame A. Okay, and so the origin that I want to select is a point that is shared by both reference frames. So it's usually the place where one reference frame is rotating around another one. So that occurs right here at the connection. So we'll call this point O for origin. For G, the origin is O, and for A, the origin, there we go, is also O. And so, we can pick any origin we want. We could have picked two different origins for two different reference frames. We could have put it somewhere else. But we're the engineers solving the problem, and we want to select an origin that makes this most convenient for us. And so, as you'll see here in a second, point O turns out to be quite convenient in describing the orientations of these reference frames. So that's a pretty good choice. So the second thing that I have to do is select a coordinate system. So for reference frame G, even though the coordinate system is centered here on the origin, I'm going to draw it over here just so that things don't get too cluttered. So I'm going to have x hat going to my right. I'm going to have y hat going up. And I'm going to have z hat coming out of the page. And if you're like me, I very easily get confused when I do cross products. There's a cross product that we're going to have to deal with in the future here. So I've just kind of memorized a little cheat that I use for cross products. So I write I hat, I write j hat, and I write k hat. You might remember that I, j, and k hat sometimes they're substituted for x, y, and z. So that's why I picked those, as they're sort of like the second favorites. And I go in a counterclockwise direction. I just draw a couple of arrows like that. There we go. Okay, and so what this means is if I'm crossing things and I'm going in the direction of the arrows, I get the third thing as the result. If I'm crossing two things and I go against the direction of the arrows, I get the negative of that third thing. So just as an example here, if we wanted to cross I hat with J hat, I'm going to start with I. I'm going to cross it with J. Notice that I go in the direction of the arrow that I've drawn. And so this is going to yield for me that third component, which is K hat. But let's say I wanted to cross K hat with J hat. Well, if I'm crossing K hat with J hat, I start at K, I move over to J, and so I definitely get I hat, but notice that I moved in the opposite direction of my arrows. I essentially went clockwise, whereas the arrows go counterclockwise. And so that moving against the arrows means that this is not only I hat, it's negative I hat. So let me put it in parentheses there. Negative I hat. So this will come in handy just as we're doing cross products to kind of remember what those cross products are and whether we end up with a negative or positive. Okay, so I've got this coordinate system. I've got my x hat, my y hat, and my z hat. Um, so let me try to describe in words what this coordinate system means here for step one. So I want to have x hat, and that's going to point along the direction of OP when theta is equal to pi. So what does that mean? Okay, well, so here's my origin O, here's P, and here's theta, right? So here's theta equals 0, here's theta at pi over 2, here's theta at pi. So this guy would be pointing straight out this way, which is, of course, in my x direction. And so that's what I mean. When theta is pi, OP is pointing directly to the right, which is also in the x hat direction. So that fully defines at least that direction of the coordinate system. I'm going to move this down a little bit so it's still on the frame. There we go. Okay, so now I need to define y hat, and I'm going to do that the same way. I'm going to say that y hat is just along OP, and that's going to be when, same thing, theta is equal to, now it's going to be straight up. So theta is going to have to go 3/4 of the way around the circle. So that's going to be 3 pi over 2. There we go. Okay. So 3 pi over 2 is when this guy rotates all the way and is pointing upwards. And so that's in the positive y hat direction. And then I'm going to move this one more time. There we go. Neat little trick here. Remembering my cross products up here, I'm going to say that z hat is just going to be equal to y hat, x hat, there we go, cross y hat. And if I remember back to my little circle here, my cross product, x hat is a lot like I hat, and y hat is a lot like j hat. So I hat cross j hat is like x hat cross y hat, which gives me k hat, which is z hat. And so z hat is just x hat cross y hat, and that is like coming out of the page towards the camera, which is that direction. Okay, so we've got that piece of it. The last thing that I have to do for step one is figure out the coordinate system for reference frame A. And so I'm going to draw that on here. Sorry, this is starting to get a little bit messy. Let me maybe put it right here. So for reference frame A, again, it's fixed at the origin, but I'm going to draw the directions of the coordinate system sort of offset here so that it doesn't get too messy. And I'm going to call this one I hat. I'm going to call this one J hat. And then out of the page, we're going to call that K hat. And I need to figure out what directions those are. So we're going to have, for reference frame A, we're going to have I hat is always just going to be along OP. And this is kind of a trick, right? In that because OP is right here, but OP is going to rotate as theta rotates. This coordinate system associated with reference frame A is always going to be fixed to reference frame A. So as this guy rotates, the reference frame and the coordinate system rotate along with it. And so it doesn't really matter what direction this is pointing in, what the value of theta is. I hat is always going to point from O to P, regardless of where this thing is oriented in space. So that's a pretty neat little trick. Um, the other thing we're going to do is we're going to figure out what k hat is. And note that k hat comes out of the page, and it always comes out of the page regardless of where this theta is, where this shock absorber is oriented in space. And so k hat just points in the same direction. Whoops. K hat just points in the same direction as Z hat does, so we'll leave that there. And then we're going to do the same trick that we did down here to figure out J hat, which is, J hat, there we go, is to just note that J hat is K hat cross I hat. And then I'm going to go back to my little cheat here and truly figure out if that makes sense. So K hat cross J hat, K hat cross I hat, yes, gives me positive j hat. So that makes sense as well, given that these are orthogonal to each other. So j hat should point positive and 90 degrees both from I hat and k hat. So it does. So that is step one, just setting up the problem and sorting out the coordinate system. So I'll call an end to this video, and in the next video we'll proceed with the next steps.